buenas tardes a todos. Les agradecemos que estén aquí. Les recordamos que vamos a hacer la transmisión por YouTube de este coloquio, por lo tanto, a aquellas personas que no estén de acuerdo en que aparezca su imagen, les pedimos que apaguen su cámara. Thank you, Professor Feng, for being here. And now Dr. Hermes Leon is introducing you to our audience. Thank you very much.
Hello, everyone. It's a pleasure to welcome our guest for today's colloquium. Professor Jonathan Feng is Distinguished Professor of Physics and Astronomy at the University of California, Irvine. He has worked on the theoretical study of dark matter and searches for new physics, and is co-spokesperson of FASER, the forward search experiment at CERN, one of the topics of today's colloquium. Professor Feng received degrees in physics and mathematics from Harvard, Cambridge, and Stanford. He joined the UC Irvine faculty in 2002 and became professor and chancellor's fellow in 2006. Professor Feng is a Simons investigator, and his research has been recognized by awards from the National Science, Sloan, Guggenheim, Simons, and Simons Foundations. About the connection between some of the previous work from Professor Feng and our institute, in particular with the Hawk group within the experimental physics department, is his theoretical work about the Earth scheming neutrino detection method that was the foundation for our experimental study using the Hawk Observatory and that was recently published. Today, Professor Feng will talk about FASER and the new forward frontier at the LHC. So welcome, Professor Feng, and thanks a lot for accepting our invitation, and please go ahead.
Great, thank you very much. Thank you for the kind introduction, and it's a real pleasure to be able to speak here. So today, yes, I will talk about FASER, which is a new experiment at CERN in Geneva. And then I will sort of expand and talk about what's really, I would say, a new frontier at the Large Hadron Collider. And so in particle physics, we speak often of frontiers, the energy frontier, the intensity frontier, etc., basically simply talking about the sort of boundaries of knowledge. And I would say there's now been established a new sort of interesting frontier, the forward frontier. And so I'll try to explain what that is and what we're doing now, and also some of the plans for the future, which may be of interest to many of the particle theorists and particle experimentalists, something you might want to get involved in. Let me say that I have a talk that is quite modular in some sense. And so if there are many questions or if I'm getting very excited and speaking too fast, please slow me down, ask questions, and I'm very happy to skip some slides and make sure we finish on time, no matter how many questions. So just please jump in. And especially if I can't see the chat and things like that, please somebody let me know if there's some question online. Okay, so the outline of the talk, I will begin with some motivations. Why are we interested in this general topic? Then I'll talk about what forward physics is and why that is particularly interesting to me, at least. And then I'll talk about the FASER experiment, a sort of supplementary part of the FASER experiment called FASER Neutrino, and then the forward physics facility, which is a completely new proposal for a new facility at CERN at the Large Hadron Collider. And then I'll summarize. So let me begin with the motivations. So I know that there are people here who are not in particle physics, and so let me begin by sort of summarizing at least part of the status of particle physics right now. This is an incredibly important time in particle physics, I would say. As I'm sure you know, the last great discovery in particle physics was the Higgs boson, which was discovered in 2012. It was a fantastic discovery. It answered many of our questions, but it did not answer all the questions. And so there are many fascinating problems that still remain. Among these are the dark matter problem. We simply don't know what much of the universe is made out of. Neutrino masses, we don't understand why neutrinos have mass and what the reason is for their small but non-zero mass. We have some hierarchy problems. Basically, some scales are much smaller than expected, and we don't understand why that is, etc. Many questions remain. And we had hoped that the LHC, where we discovered the Higgs boson, would not just simply discover the Higgs boson, but discover many other new particles which would help us answer some of these questions. For example, maybe discover a particle that could be the dark matter. But unfortunately, we have not discovered any other evidence for new particles at the Large Hadron Collider. Now, what are we doing now? Well, at the Energy Frontier, which is basically in Geneva now, is in the CERN laboratory, the Large Hadron Collider. We are waiting right now. So we are currently in what's called long shutdown 2. And we will start up again probably in July and run for about 10, 15 more years, or maybe even 20. Here's a figure showing basically the years on the bottom here. And then let's focus maybe on the blue here, which is the integrated luminosity, basically the amount of data that's being collected at the Large Hadron Collider. And so in 2010, the collider began operation. Just even after the first 2 years, enough data was collected to discover the Higgs boson here. Then there was this long shutdown 1. Then more data were collected here. Now we're in long shutdown 2. This was supposed to end in 2021, but because of COVID, it extended this shutdown. And so we're starting up in the middle of 2022. But you see that we will start gathering data very soon. And then there are various planned shutdowns and more data, shutdown, more data, shutdown, more data. The interesting thing, though, is number one, we are nowhere near the end of the LHC program. In terms of years, we're sort of at the midway point. But even more important, in terms of the amount of data being collected, you see that we expect to collect data at a much higher rate in the future years. And so in some sense, we're only like a tenth of the way through in terms of the amount of data being collected. And so it's a very interesting question that you can ask, will we find these new particles that we expected, that we hope for in the coming runs up until, say, 2040 or not? And, people speculate about these sort of things, and it's sort of a very common game to play. People, have various theoretical prejudices of yes or no. The much more interesting question to me and people who work in the field is, what can we do now to enhance the prospects for discovering new physics? So instead of just, sitting around, sitting on our hands, hoping for the best, what should we do now so that we make use of this 9/10 of the data that's coming still, instead of finding out, say, in 2040, that, boy, we should have figured something out earlier because now we're all done. If we had done something over here, we could have enhanced our prospects for discovering new things. So if we look forward and ask, what is the best thing we should be doing now? Oftentimes, a very good strategy is to look back into the past and see what lessons we could learn from that, right? So this is actually a very interesting time to look backwards in terms of collider physics, because last year was actually the 50th anniversary of the birth of hadron colliders, of the birth of basically smashing together two colliding beams of protons. So what was that? Well, in 1971, 51 years ago, CERN's intersecting storage rings, the ISR, had a circumference of about 1 kilometer. So, enormous for that time, small by comparison to now, but enormous at that time, and collided protons with protons at center mass energies of 30 GeV. Now we're up to, much higher, hundreds of times higher, but at that time it was the leading machine, 30 GeV. This is a diagram showing this intersecting storage rings idea. This is a photo of it from the early times, 70s. And just to set the sort of time scale here, this is a plaque down at the ISR, which notes that Werner Heisenberg actually inaugurated the machine. So it gives you a little bit of a sense of how long ago we're talking about. 50 years is quite a long time. Now, on occasion of the 50th anniversary of the ISR, many people organized conferences to look back at the legacy of the ISR. People wrote articles about it in various trade magazines like the CERN Courier. And it was fascinating for me to read. Obviously, I wasn't really around at that time, but it was very interesting to hear some of the sort of most eminent physicists now who were just starting their careers in their 20s back in those days talk about the legacy of the ISR. And I would say 50 years is a fascinating amount of time, because after 50 years, you know, these people are all very well established. They're not in danger of losing any of their reputation or their prestige, and they just simply tell it like it is. There's no spin. They just simply tell you the facts. And so here are some excerpts. Steve Myers, who was a very prominent player at CERN for decades, said the ISR had enormous impact on accelerator physics, but sadly little effect on particle physics. So he just says basically it had very little effect on particle physics. Lynn Evans, who's sort of the architect of the LHC, Peter Yenny, another very famous particle experimentalist, they wrote a little bit more detail. They said, there was initially a broad belief that physics action would be in the forward directions at a hadron collider. It is easy to say after the fact, still with regrets, that with an earlier availability of a more complete experiments at the ISR, CERN would not have been left as a spectator during the famous November Revolution of 1974 with the J-psi discoveries at Brookhaven and SLAC. So what they're saying is that at the Hadron Collider, they were, it turns out, we now know, were creating new forms of matter, in particular this J-psi particle and the charm quark. But because there was theoretical prejudice that all the interesting physics would be in the forward direction, the detectors did not actually completely cover all of the interaction region. They were focused on the forward direction, and for that reason, they missed this key discovery. And I mean, for those of you who don't know, the discovery of the J-psi is one of the sort of watershed moments in particle physics. It broke open the floodgates to a whole new era of particle physics. And it's really, you know, something that people at CERN regret, that because of this oversight, instead of it being discovered in Europe, the J-psi was discovered in the Americas at Brookhaven and at SLAC. So this is, I think, a cautionary tale. You know, it's a real shame to build a fantastic collider and be producing new particles and somehow miss them simply because of theoretical prejudice. So an obvious question then is, are we missing opportunities in a similar but opposite way at the LHC? That would be obviously something we'd want to fix. In contrast to the ISR days, there is now broad belief that the most interesting physics is at high transverse momentum. So what I'm saying here is that in the ISR days, you can actually kind of even see it here. If you were to have collisions here at this point here, forward directions are basically along this direction, and then transverse directions are along this direction here. And the point of these people is that everyone expected all interesting physics to be in the forward direction and didn't bother looking in the transverse direction, and so missed the charm discovery. And so nowadays, because perhaps we've learned our lesson from the ISR, we have incredible coverage at transverse directions. Okay, so here's, for example, the Atlas detector at the LHC. So this sort of red axis here is where the protons come in, collide together. And if they make something that produces transverse particles, we have a several $1 billion worth of detector ready to detect that sort of stuff. Okay. However, if we actually have interesting physics in the forward direction, that is, that it's produced here, but then travels in the same direction as the beams, the proton beams, then actually we will miss it. So basically, we have become very good at detecting transverse physics, but we've sort of made the opposite mistake now, that we don't cover the forward region very well. And this is not just a small oversight. It turns out that we know that there are enormous fluxes of neutrinos going down the beam pipe. Other mesons, light standard model particles, are going down the beam pipe, and we're simply missing the most energetic of these because we don't cover the forward direction. And in fact, we could be missing many other particles. We could be missing particles known as dark photons, axion-like particles, milli-charged particles, dark matter itself. There are many theories that predict that the dominant flux of all these particles is in the forward direction, up and down this red axis, as shown by the arrows here. And simply because we're not covering these, we may be missing those. So we may be making exactly the opposite error that was made at the ISR by covering this direction, but not the forward direction. Now, is this an important problem? Well, let me try to emphasize it another way. If we were going to look for new particles, we could, at very sort of broad, rough level, we could put them in this plane where we have the mass of the new particle here and the interaction strength of the new particle here. Now, if you do this, then you can ask, well, where do we expect new particles to show up? So particle colliders basically shine a light on this plane from the upper left corner. So things that are light, things that interact very strongly, we're good at finding those sort of things, okay? So actually, in this upper quadrant here, we have particles that are already discovered. So for example, the electron is a particle that has an MeV mass, has an interaction strength of order 1, and it was here, and of course it was discovered in 1895, ancient history. But, you know, even particles like protons are here, quarks are all here. There's a whole bunch of particles that we've discovered, and they're all in this sort of upper quadrant. Particles down here are impossible to discover. They're either, well, they're both too heavy and too weakly interacting. So you simply have no rate. You can't produce these. We don't have high enough luminosity, high enough energy colliders to see these sort of things. So they're simply impossible. And so all the interesting action, the frontier, is along this diagonal. Up here, there's the strongly interacting heavy particles, which are things like, well, the top quark and even the Higgs boson can go in this category. They're sort of up here. Speculative ideas like supersymmetry, extra dimensions, things like that are also up here. And we've been thinking about that for a long time. But sort of new to the game is that there is an entirely different part of the diagonal here, which is weakly interacting light particles, which are also at the frontier of discovery. They could exist, but we haven't seen them yet. But at the same time, we could see them if we look hard enough. And if I were to sort of put this in context, I would say that the field has largely tried to basically move down this axis with particle colliders. This is E.O. Lawrence, who in the 1930s, invented this idea. And we basically had incredible success building bigger and bigger colliders until we get to the LHC, until we're at this point, just looking for particles that interact very strongly and have heavier and heavier masses. What's been neglected relatively is this direction, pushing down to light particles with weaker and weaker interactions, which are a perfectly viable idea. This has been the traditional target of big science up here. LHC has been looking up here intensely for years. It turns out that down here, you can actually see these new particles with much smaller experiments and much less investment in resources, much cheaper, much faster, as I'll show you. And this I would call the sort of legacy of Fred Reines, shown here. He's the discoverer of the neutrino, and I am sort of honor-bound to mention his name because I'm actually sitting in the Fred Reines Hall. He was a faculty member here at UC Irvine and one of our sort of great leading figures. He discovered the neutrino, and the question is, are there other particles down here, light, weakly interacting, which maybe we've missed, but we should be able to find if we try harder. Okay, so let me skip this and just give an example. So where might some particle like this come up? So let's say that we have something called a dark sector. So this SM here stands for standard model. And in the standard model, we know we have various interactions like electromagnetism, of course. But we know that this is not the complete story of physics because there are new particles in the dark matter. So there's some dark particle out there, and it's quite possible that's it sitting in its own sector of particles, the dark sector, which I draw over here in a different box. This is meant to indicate an entirely different group of particles, which include X, the dark matter, but possibly also other dark forces, which only sort of interact with dark matter and its dark sector particles. They don't have any impact over here. And there could be even a dark electromagnetism. There could be dark matter scattering off of dark matter through sort of Rutherford scattering over in this dark sector. We just simply don't know. Now, why do I mention that here? You might say, well, okay, this is sort of a nice fact that we have the standard model, we have the dark sector. We knew we had to have dark matter, so it's over here, and maybe it has some interesting dynamics with some interactions. But basically, it does nothing to us over here because this is just interacting at most gravitationally with us. However, it turns out that if you have a dark electromagnetism and you have the standard model electromagnetism, these forces can interact through this sort of operator. This is the field strength tensor F mu nu for standard model electromagnetism. This is the same thing, but for the dark electromagnetism. And this operator actually mixes the dark photon, that's what this is called, with our photon. And so one can go through and just imagine what happens if this happens. And Bob Holdham did this many, many years ago. And it turns out there are two interesting possibilities. One is that there are dark photons, some new particles that are just like photons, except they have a mass, which is an unknown free parameter, and they have a coupling to everything that's charged suppressed by some small parameter epsilon, which is another free unknown parameter. Okay, but then what this is saying is that instead of just having a photon, you have a massive photon, which can actually be seen in the same way as the photon can be, except it's typically much more weakly interacting. Another possibility that flows out of this is called mealy charged particles. It turns out if this side over here was a massless thing, its impact is to basically have particles over here show up in our sector as if they're mealy charged. They have sort of 1,000th of the charge of the electron or a millionth, some very small parameter. So this motivates them looking for these two things, these dark photons, these mealy charged particles, and they would, if they were discovered, be immediate evidence of a new force, but they would also likely be the first glimpse we have of the dark sector, which of course would be, sort of the holy grail of particle physics at the moment, try to figure out what most of the matter in the universe is made out of. Okay, so I hope this sort of sets the motivation that we want to look for light particles, and the LHC is not very good at it at the moment. So are there any questions before I go on? Okay, so we want to look for new light particles. So as I've kind of been hinting, but let me just say it outright. If new light particles are light and weakly interacting, the existing big LHC detectors are perfectly designed not to see them. Basically, we have designed incredible detectors which have a huge blind spot, which is going to miss all these particles. So these existing detectors are designed to find heavy particles, like I mentioned, things like supersymmetry or, new quarks, like the top quark, something very heavy. These particles are produced at low velocity, so you basically get a proton. To hit a proton, you make something very heavy. Because all of that kinetic energy went into making rest mass, there's not that much energy left over for velocity for this heavy particle. So it's kind of moving at some low velocity. Then when it decays, it just decays basically isotropically And so you get a whole bunch of particles transverse to the beam, and you can find those, and that's what we've been searching for decades. But if you had new light particles, these are mainly produced in the decays of light existing particles, like pions, etas, kaons, D and B mesons, all these very well-known particles, which are all very light compared to, say, the Higgs boson or the top quark. These particles are mainly produced along the beamline, along these red directions, and so the new particles basically disappear through the same holes that let the beams in. So you have a hole here to let the proton beam come in, the proton beam come in, collide in the middle here. And what we're saying is that most of these particles then just go right back out the same hole that the protons came in. And if they are decaying to or producing new particles like this dark photon, basically all the dark photons are just pouring out the same hole that the protons came in. And so you're just missing them. So clearly what we need is we need to detect particles that are flowing out in the red direction, basically exploit this wasted inelastic cross-section of 100 millibarns and cover the blind spot in the forward region. Now, if we go and try to just put a detector here, obviously that's not going to work because you're going to block the proton beams. So the protons won't be able to come in and you won't have any collisions in the first place. But the simple observation is if you go far enough down the beam line, at some point these protons will curve away because, of course, the LHC is a circular collider. And so eventually magnets will take the protons away. But particles that are going straight out the beam line, they will actually just go straight and they will just go into your detector if you put it far enough away. So this is the essential observation that I and 3 postdocs made about 4 years ago. So we got very excited and we went and looked around the LHC ring. So here's the LHC ring here. And if we focus in on this part right here, this is the Atlas detector. And what we're saying is that there are particles that could be produced at Atlas and then just stream straight out tangent to the LHC without being detected, and we'd like to detect them. And what we noted is that here is a side tunnel where you could actually put a detector without having to dig a new tunnel and see these particles. So this is maybe a slightly better view. This is from the aerial view from the top. Here's the Atlas detector. The LHC is this blue line. And you see that after several hundred meters, this blue line starts curving because we need to make the circular collider. But particles like the dark photon and other new weakly interacting particles will just pass in a straight line through all this rock. They won't be changed by the magnets. They'll just go straight. And they could, in principle, go right through this side tunnel, this blue tunnel here. And so I still remember this. We were very excited to discover this. And we asked someone to go down to the LHC tunnel and take a photo. This is what it looks like. If you go to this cavern, UJ12, and you look to the west, what you see is this. You see that there is the LHC beam, which is the proton beams in it, which is going down this blue pipe here. But there's this side tunnel, TI12 it's called, which is actually where the tangent line to Atlas goes through. And there could be a huge flux of new particles passing through this tunnel because that's the straight line from Atlas. And what we basically realized is that if you could just put a detector here, you could actually maybe detect almost for free a bunch of new particles that have been escaping every other known detector at the LHC. So here's a little video to show what I'm talking about. So this is the giant LHC beamline. This is Atlas right here. And what we're going to do is we're going to sort of swoop in and follow the trajectory of a particle that's produced at Atlas, but that just goes straight and doesn't get bent by the Atlas, by the LHC magnets. Okay, so let me play it and hopefully you can see what I'm talking about. Okay, so we swoop in here and pass right over Atlas. And there you go. So let me do that again. Maybe I can put it on pause. So right here is Atlas, and so a particle would be produced at Atlas, and then would go straight. Here's the LHC beamline, and as you see, it curves away to the left, but these particles are very weakly interacting, and they would just go straight into this side tunnel right here. And so the objective then is to put a detector there in that side tunnel. Okay, so I hope that video was visible and clear to everyone. Now, important question anyone would ask is, how big does the detector have to be? So what we're proposing is basically going, it turns out that detector, that side tunnel is about 480 meters away. And so an obvious question is, if you have to put a detector so far away, it better be enormous to capture enough solid angle to actually intersect enough particle flux. And the rather amazing thing is that no, it doesn't have to be enormous. So the particles we're trying to detect, say maybe resulting from pion decay, they have a momentum which is governed by the LHC, a TeV momentum. And then their transverse momentum is just governed by the pion mass. So it's 250 MeV or lambda QCD for the particle physics experts. What this means is that if you actually ask the length scales involved, when that particle travels 480 meters, it's only deviated from straight ahead by about 12 centimeters. Okay? In other words, the opening angle of this beam of particles we're looking for is 0.2 milliradians, which is a pseudo rapidity of 9. You can compare that to the moon, for example, which is 7 milliradians. So if you look at the moon in the night sky, that spot is far, far larger than sort of the angular spread of the particles we're looking for. Another way to say it is that you can basically hold up a typical sheet of paper that you would write on, put that at 480 meters away, and most of the particles that we're looking for will actually pass through that sheet of paper. Okay, so it's an incredibly collimated, focused beam of particles. And so you don't need a large detector, you just need to put a small detector in the right place. And so, basically these red lines I'm showing here are far more dispersed than is actually true. If I were to draw the actual reality, it'd be an extremely thin one arrow line that would show the trajectory of most of the particles we're looking for. Okay, so now let me get to the fun part, which is I can tell you what we've actually done. So we basically, motivated by what I've just told you, decided to build a detector at the LHC. And so, as I said, just 4 or 5 years ago, this was an initial proposal by me and 3 postdocs who are all theorists. And basically, things proceeded very quickly, at least on the timescales of LHC detectors. So we submitted a letter of intent to the CERN LHC committee. Then this effort was greatly helped by the fact that we have a very small detector. I'll show you what it looks like. But basically, we borrowed parts from the much bigger detectors who were very kind to lend us various spare parts. And so much of it didn't have to even be built. Basically, we just recycled existing detector parts. We obtained some incredibly important funding from private foundations, the Heising-Simons and the Simons Foundations. And then we were finally approved in 2019. And we fully constructed and installed this thing about a year ago and have been now commissioning it. And it's basically ready to go to actually look for new particles as soon as the LHC turns on in a few months. This is the first FASER collaboration meeting. I show you this because for many of you, you know that LHC detector collaborations are typically thousands of people. 5,000 people sign a typical Atlas or CMS paper. Our collaboration started off much smaller. There's about 20 of us here. It's now grown to about 70, but it's still in a very, very small group of people compared to the big collaborations. We have about 21 institutions involved in the project right now from 9 different countries. And this is the detector we ultimately built. So just to explain what we're looking for, we basically are looking for this possibility that some particles produced at Atlas, it comes streaming in the forward direction, very collimated, and it passes through all the walls and the rock and the concrete. It's extremely weakly interacting. And then it can decay to, say, an electron and a positron. And so we built a detector, which is a tracking detector, and it can look for electrons and positrons in this particular direction. So it's sort of look like a telescope almost, because we just point it straight at Atlas, except we're pointing it at 100 meters thick wall and looking for the very rare events that come through. Obviously, this is very helpful because this 100 meters of rock basically kills off most of the standard model background. And we're able to basically eliminate the rest of the background with some scintillators. We veto on scintillators that have charged tracks coming in and various things. But anyway, the bottom line is this detector is only about 5 meters long, and it's very good at looking for these light weakly interacting particles. So this is a bit of a, history here. In 2019, this is this side tunnel. It had been completely disused. It was actually condemned. You weren't allowed to go through this door here. It had ventilation pipes and stuff like this. In spring of 2020, we dug out a little trench here so that we could put the detector exactly on the line of sight of this beam collision axis. Very interesting story. This is an Italian company that excavated this for us and actually finished literally hours before they were told to leave the site because of COVID. But anyway, luckily it was done just in time, and they came back later and neatened it up, and this is what the trench looked like in summer 2020. We have magnets basically so that the positron and electron tracks are separated slightly, so we can tell that there's two particles there instead of just one. And these were built for us by the CERN Magnet Group. Here's some scintillators that were used to veto incoming muons, basically to remove the dominant standard model background. And then this was what it looked like just about a year ago. So here we're standing looking for Atlas. So you see the line down here. If you look very carefully, you can see it kind of curving away because of the curvature of the LHC. So Atlas is, 5 football fields in this direction. And then here is the side tunnel, which was previously empty, and now we have the phaser detector there. This is a slightly better view of the detector. Basically, Atlas is in this direction, particles come in here, and we're looking for E plus E minus tracks to come through here. And, lots of cables and things, but essentially it's a very simple detector, and as I say, it's only about 5 meters long. So what are we going to do? As soon as the LHC turns on in July, we will start collecting data. And I can't show you all that the phaser can do, but basically just to show you one example, this is dark photon parameter space. So you have this unknown mass of the dark photon here, this unknown coupling strength here. And all the gray region is excluded by other experiments, current bounds. So this is all excluded. This top part is all excluded. And then the yellow is where FASER will be able to probe in the coming months with the various data collected here. So 1 inverse femtobarn, which is basically 1 week of running, we are already starting to probe new parameter space that no one has covered before. And then as we continue on running longer and longer, we will push out into more and more parameter space with the opportunity to discover something. And so this is kind of interesting. If you look at the plot that I showed at the very beginning of the amount of data collected, what we're saying is that as soon as we start basically collecting data and this curve starts rising, we will have the potential to discover new particles. And obviously, the potential just increases as we go along this curve here. So that's very nice. If you look at something in a new way, you can actually discover it with very little data. And so that's what we're hoping to do. Now, let me move on to describe a few other things that have happened. So in addition to FASER, there's another detector called FASER new for neutrino. And let me explain what this is supposed to do. So I've talked about looking for hypothetical new particles. Obviously, if we discover any of those, it would be completely revolutionary, but we're by no means guaranteed to. You might note, however, that in addition to hypothetical light weakly interacting particles, there are also known light weakly interacting particles, the neutrinos. Turns out that no neutrino produced at a particle collider has ever been detected before. And the first reason for that is simply that neutrinos are extremely weakly interacting. They pass through, many meters. They can pass through the entire Earth without interacting, etc., etc. And so it seems to have been sort of a assumed fact that you will just never, ever detect a neutrino produced at a collider. There are just not enough of them. Turns out, however, that that's not actually a true statement. The real reason that we haven't detected a neutrino at a collider is that we haven't been putting the detectors in the right place. The highest energy neutrinos, just like dark photons and other hypothetical things, the highest energy ones actually pass down the beamline. And those are actually the ones that are the most highly interacting. So it's not true that we haven't seen neutrinos at colliders because they're just impossible to detect. The actual reason is that we've been putting our detectors in the wrong place. You should put them in the forward direction because that's where the highly interacting, highly energetic neutrinos are. And of course, that just plays right into the hands of FASER because that's where we're putting the FASER detector anyway. So what we've done is actually looked for neutrinos in the forward direction. And as I'll mention, we have actually seen some. This is actually a fascinating new discovery because what it's saying is that there's an entirely new program at the LHC, namely Lhc Neutrinos. And it turns out the neutrinos that we're going to detect at the LHC are the highest energy that have ever been made by people, TeV energy neutrinos. And it turns out also that we can detect all the different kinds of neutrinos. They come in different flavors, nu mu, nu e, nu tau. We can detect both neutrinos and antineutrinos. We can distinguish the two. And so we can do, for the experts, studies about lepton universality and CP violation, for example, in the neutrino sector. So how do we detect these? Well, in 2018, basically as a preparatory step for FASER, we took an emulsion detector, shown here, very small, had a mass of about 11 kilograms, and we collected data for just 4 weeks. Basically, there was a technical stop at the LHC. We ran down there, dropped this box in the forward region, and got out of there before the radiation levels went up again. A month later, there was another technical stop. We ran down there and picked up the box and analyzed the data. And in May 2021, we showed that in this emulsion data, we've actually detected an excess of 6 candidate neutrinos above 12 expected neutral hadron background events, which is a 12.7 sigma signal. So this is not, a 5 sigma detection, but it basically tells you that it's a completely doable thing. You just have to put your detector here in the right place, and you will be able to detect neutrinos from the LHC. In other words, to try to put it in the most stark way I can, when it comes to neutrinos, just like so when it comes to real estate, location, location, location are the 3 most important qualities. We took this FASER pilot detector, which was a suitcase size detector, put it in the forward direction for 4 weeks using $0. It was again recycled parts, and we detected 6 candidate neutrinos with this tiny little box. That's to be contrasted with every other collider detector ever built. Here's some examples from the last 3 decades. All these previous collider detectors, many of them were building size, enormous 6-story tall detectors, took decades to construct, and billions of dollars went into their construction. And all of these detectors have detected 0 candidate neutrinos, basically because they're not suited for it. They're not looking in the right direction. And so we find this to be very promising in terms of future prospects. So in the future, what we're doing is we're basically putting a dedicated neutrino detector in the front of FASER called FASER New. And instead of being a little suitcase, this thing is actually a ton of tungsten. And so we'll have much higher event rates. Just to give an example, this is for electron neutrinos, muon neutrinos, and tau neutrinos. And what's shown here is, as a function of the energy of the neutrino, how well we know its interaction cross-section. Okay, so this is cross-section on the y-axis here. And you see that existing data, which is in the gray here, we have some data for nu E up to basically 200 GeV. Similar story for nu tau, except much worse. We've only detected about 20 tau neutrinos up to about an energy of 100 GeV. Muons, we go up to 300 GeV, not that much better. And then we have some astrophysical. Ice cube detects neutrinos, and so is able to do 6 TeV and higher. But the point is that in the middle here, at sort of a TeV energy, there's just no direct data on neutrino interactions. And at the same time, what's plotted here in the color is what FASER New will be able to do after we run for 3 years. Basically, in 3 years, we will have detected 10,000 new mu's and 1,000 new e's and even about 30 new tau's. And so we will be able to fill in this gap and explore neutrino properties at TeV energy, and also basically distinguish nu tau from nu tau bar, for example, for the first time ever. So anyway, we'll be able to do neutrino physics, and this is guaranteed physics. This is standard model physics, although of course what the neutrino properties are could be different from what we expect. There's also the ability to probe QCD. I won't go into great detail here, but we can also probe QCD at extremely low Bjorkane X, 10 to the minus 7, for example. So let me go on, given that I have not that much time. What's happening in the future is we're proposing something called the Forward Physics Facility to basically make use of these sort of things, but do it in the right way. So FASER and FASER New and other proposed fire-forward detectors are, basically we're retrofitting something that never was intended in the first place. No one building the LHC ever thought that we should put detectors where we're putting them. And this leads to extremely cramped conditions because we're putting detectors where, everyone thought it was like a service tunnel for walking in or something. And so we have very tight constraints. What we like to do is actually make bigger detectors, but that requires a large cavern to actually do this in the right way. And so this big cavern is called the Forward Physics Facility. It will be designed to house a whole suite of experiments in the right way, and we're hoping that it will be done in the next, say, 7 years, so we can collect data during the rest of the LHC. We've had a number of meetings to organize this every 6 months in the last 2 years. If you're interested, there are 2 summary papers now out. One is the short paper, so-called short paper, 75 pages, and then a much larger comprehensive document, which was prepared for the snowmass prioritization process that's in the works in the US here. And that is, here are the archive numbers. But basically, what has been proposed is to build this forward physics facility. So this is, again, Atlas, where the particles are produced. And if we go out along this line here, there is actually an open field which is on CERN land and on the French side. Basically, we're going to build a shaft that will take us down to the level of the LHC. And then we can build a cavern, which is about 65 meters long, and put a number of experiments in there, and basically have a dedicated facility for forward physics here. This has been now designed in some detail by the CERN Civil Engineering Department. This is what it looks like. So basically, you take these stairs down 88 meters, and this is the cavern. As I say, it's about 65 meters long, and it has room for larger detectors, sort of upgraded detectors like the FASER, we'll call it FASER 2, FASER New 2, but also other ones. And we're envisioning putting a liquid argon detector here, a bunch of scintillator bars for looking for milli-charged particles, but basically doing this right in some sense, having a dedicated facility to house a bunch of far-forward experiments. This is some more of the work that's been done by the civil engineers in terms of building or designing the surface buildings where we would assemble the detectors and drop them down this shaft. This is where it would look. It's a greenfield site right now. We would put this little building here. And we even have a cost estimate for this, which is very preliminary, but it's roughly speaking comes to about 40 million Swiss francs with significant error bars here. And to that must be added also the experimental costs, building the experiments. But anyway, that's the cost. And then the timeline, we of course want to have this in place by the time the high luminosity LHC starts running in 2029. And so the idea would basically to dig the tunnel, do all the pure civil engineering work in the next few years. At the same time, get the experiments ready and install services at the beginning of the high luminosity run 4, and then basically put the experiments here and basically collect data for about, say, 10 years for most of the rest of the lifetime of the LHC. Okay, I think I'm about out of time, so maybe let me just show this. At this point, the FPF has been attracting a fair amount of attention from hundreds of people, and there's a very well-established physics case for it. It includes both sort of guaranteed standard model physics as well as speculative BSM physics. And this shows some of the topics that are covered. We can look for new particles. We can actually detect dark matter in this thing. There's QCD studies, neutrino studies. Actually has very interesting implications for astroparticle physics, including, cosmic rays and the things that are of great interest for Hawk. And here are some of the individual topics in here where the FPF could actually contribute significantly. But given the lack of time, I won't talk in detail about these, but there's some very interesting topics which the FPF could contribute to. So let me jump to the summary here. So if I had to summarize in a slide what I've been trying to say, it is that at the moment, there are standard model and beyond the standard model physics opportunities that we're just simply missing in the far forward direction at the LHC. And again, it's a very simple observation. The observation is that there are huge fluxes of known particles and also unspeculative particles, which are just highly focused in the forward direction, and we are missing them because there's no detector covering the far forward region. In the last 3.5 years, basically on a very fast track, we have tried to remedy the situation a little by building FASER and FASER New. These are detectors that are only a total of about 5 meters long. The total cost in terms of hardware was just $2 million. And along with another experiment I haven't even mentioned, but S&D at LHC is another important experiment. We will start data taking in the mid-2022s, basically in July. And the one thing that is for sure is that we will create a new field of LHC neutrino physics, and we will also look for many new particles. In the future, we would like to do this in a more sort of planned out, comprehensive way. And so the Forward Physics Facility is a proposal to basically fully realize the high luminosity LHC physics potential for both of these physics cases. Very preliminary cost is 40 million Swiss francs, which, compared to the costs that have been already sunk into the LHC is really very affordable. And this we have to build experiments too, but the total I would suspect is probably not more than, I don't know, maybe double this or so. So anyway, that's the plan. We are working furiously on this. Invite anyone interested in looking into it and joining us. And construction can take place basically completely separate from the LHC. So one of the nice things to point out here is that this entire topic is just parasitic to the LHC. We do not require modifying the LHC. The point is simply that the LHC has been built. It is possibly producing millions of dark photons. We just need to put detectors in the right place to see them. And so it's a completely almost separate project from LHC running. We can build this cavern, we can build these experiments while the LHC is running. We can install them, we can work on them, we can service them. And so it's a nice project that is sort of independent of the LHC. Okay, I think that's it for me. Thank you.
Thank you, Professor Feng, for a very interesting talk. I think we have some time for questions. Yes, please, Andres.
Yeah, very interesting talk. Thank you very much. I wonder if in the other interaction regions, you can also profit from forward detectors. Can you just place your emulsions in front of Alice or in front of other interaction regions? Is there any project at the moment going on?
So there isn't. So all of the let's see if I go back here. So at the moment, the existing efforts are this FASER and FASER new, which are in this little side tunnel here. And then is S&D at LHC, which is in this side tunnel here, which is on the symmetric side of Atlas. And, the reason Atlas is sort of picked out is just simply because there's a lot more infrastructure around here with the SPS and things like this. And so there happen to be these side tunnels that are conveniently located. There is possibly interest in doing this elsewhere, but typically, for LHCb, Atlas, typically there are lower luminosities. So if we're just trying to maximize the amount of data collected, I think most people have considered CMS and Atlas as the sort of first things you would look for in terms of interaction points. I should say for the Forward Physics Facility, this completely new idea, the CERN Civil Engineering group actually went all around the LHC and looked for suitable locations, doing things regarding, where there was property that was on CERN land, even doing things like looking at the structure of the rock and stability and things like that, sort of, very detailed civil engineering studies. And after considering many, many candidates, they settled on this particular one, which is right here.
Okay, thank you.
Yeah, thank you.
And do we have more questions? If not, maybe I can make one. I was wondering if there is any difference or advantage of also taking data during the heavy ion runs at the LHC with FASER or FASER new?
Yeah, now that's a very interesting question. So we will take data during those runs because we'll just be on. So there's no point in turning it off. Again, the luminosity collected is typically low, right? Because these heavy ion runs are sort of done in the last month of the year and not very long. And so it's not that easy to find particles that won't appear in the PP collisions that would appear in the heavy ion runs, right? So we don't know. Could be that we're just simply not creative enough, but so far we haven't found a strong physics case for it. But on the other hand, we are simply going to collect data then because we don't have to do anything. We just have to leave the detector on. And I mean, another thing I haven't mentioned, but all the particle physicists will appreciate, we are in an extremely low rate, quiet place, right? We are behind 100 meters of rock. We have typically event rates of like 500 hertz or something. So keeping the data, writing it all to tape and everything is no big deal. And so we just basically keep everything that comes through. And so we will certainly collect everything that comes through during the heavy ion runs too.
Great, thanks.
Yeah, thank you.
So we have more questions. If anybody wants to ask in Spanish, I can make my best to try to translate it. So feel free to do it. I don't see any more hands or questions. Well, if not, thanks again for this very interesting talk. It was really nice, these proposals for the experiments.
Well, thank you very much. And thanks for your attention, everybody. Appreciate it.
Thank you for being here, and thank you, Hermes, for conducting the colloquium.
Yeah.
Nice to meet you.
And Hermes, thanks so much for mentioning the earth-skimming neutrinos at the beginning. That's a topic I love greatly, so it's wonderful to hear about that.
Thank you. Yes, I mean, we are fans of your work here. So.
Well, thank you. That's great to hear. Made my day.
Thank you so much. And bueno, pues muchas gracias a todos. Que estén muy bien y nos vemos en el próximo coloquio. Thank you so much.
Thank you.
Bye-bye.
Bye.